My dear students, welcome back to our channel. In this video, I will be explaining the MBA second semester subject Quantitative Analysis for Business Decisions as prescribed by JNTU and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 2 first important short question is: what is a dual LPP? In linear programming problems, LPP, every problem has another related problem called its dual. The original problem is called the primal, and the related one is called the dual. Both are connected, and solving one gives useful information about the other. The primal usually focuses on maximizing profit or output, while the dual focuses on minimizing cost or resources. Example: a factory wants to maximize profit by producing chairs and tables, primal. The same situation can also be seen as minimizing the cost of wood and labor needed to make those products, dual. Both problems give the same final result, but from different viewpoints. Why is it useful? If the primal is difficult to solve, the dual may be easier. It helps managers see both profit side and cost side of a decision. So, dual LPP is like looking at the same problem through two different lenses, profit and cost. Next important short question is: to mention the limitations of LPP. Limitations of linear programming problems, LPP. Linear programming is a powerful tool, but it has some limitations that managers should know. 1. Assumes linear relationships. LPP assumes that cost, profit, and other relationships are straight lines, which is not always true in real life. For example, increasing raw material may not always increase production at a constant rate. 2. Single objective only. LPP deals with one goal at a time, like maximizing profit or minimizing cost. Real problems may have multiple goals. 3. Certainty assumption. LPP assumes all data, cost, demand, resources is certain and fixed, but in reality, these may change. For example, market demand may vary unexpectedly. 4. Ignores human and social factors. It focuses only on numbers, ignoring employee morale, skill, or customer satisfaction. 5. Not suitable for complex nonlinear problems. LPP cannot handle problems with curves or complex relationships. Conclusion: LPP is useful for simple, well-defined problems, but managers must be careful about its assumptions and limitations. Next important short question is: 3. Write any two assumptions of LPP. Two assumptions of linear programming problems, LPP. Linear programming problems, LPP, are based on certain assumptions to simplify real-life problems. Two important assumptions are: 1. Proportionality, linear relationship. It is assumed that the contribution of each variable to the objective, like profit or cost, is directly proportional. Example: if producing one chair gives 500 rupee profit, producing two chairs gives 1000 rupees. The increase is linear. 2. Certainty, deterministic environment. It is assumed that all coefficients in LPP like cost, profit, resource availability, and demand are known and fixed. Example: a factory knows that producing a table uses 5 units of wood and 2 hours of labor exactly, without any variation. Conclusion: these assumptions make LPP simpler and solvable using mathematical methods. However, in real life, relationships may not always be linear and data may not always be certain, so managers should apply LPP carefully. Next important short question is: 4. What is the extreme point method? Extreme point method in linear programming. The extreme point method is a way to solve a linear programming problem, LPP, graphically. It is based on the idea that the optimal solution, maximum or minimum value of profit cost, occurs at one of the corner points, extreme points, of the feasible region. Steps in simple words. 1. Draw the constraints on a graph. 2. Identify the feasible region, area satisfying all constraints. 3. Locate all corner points of this region. 4. Calculate the objective function, profit or cost, at each corner point. 5. Choose the corner point giving maximum profit or minimum cost. Example. A small factory makes chairs and tables. By plotting constraints of material and labor, the corner points are 0, 0, 0, 10, 8, 0, and 5, 5. Calculating profit at each, the point 5, 5 gives maximum profit. Conclusion: the extreme point method is easy, visual, and effective for two variable LPPs and helps managers quickly find the best solution. Next important short question is 5. Define primal and dual problems in LPE. Primal and dual problems in LPE. In linear programming problems, LPP, every problem has a primal and a dual form. 1. Primal problem. The primal is the original problem, usually about maximizing profit or output. Example, a factory wants to produce chairs and tables to maximize profit given limited wood and labor. 2. Dual problem. The dual is a related problem, usually about minimizing cost or resources. It looks at the same situation from a different angle. Example, the same factory wants to minimize the cost of wood and labor needed to produce the required number of chairs and tables. Relationship between primal and dual. Both give the same optimal solution from different perspectives. Solving one can give useful information about the other. Primal focuses on outputs and profit, dual focuses on resources and cost. Conclusion: understanding primal and dual helps managers see problems from two sides, making decision-making smarter and more flexible. Next Unit 2. Long questions. First important long question is: explain the application areas of LPE with examples. Application areas of linear programming problems, LPP. Linear programming problems, LPP, are widely used in business, industry, and management to optimize resources, reduce costs, and maximize profits. Its application areas include 1. Production management. LPP helps decide how much of each product to produce with limited resources like raw materials, labor, and machine hours. Example, a furniture factory uses LPP to decide the number of chairs and tables to produce to maximize profit given limited wood and labor hours. 2. Marketing and sales. It helps in product mix, pricing, and sales planning. Managers can choose the combination of products that maximizes revenue. Example, a soft drink company decides how many bottles of cola and orange soda to produce based on demand and available production capacity. 3. Financial management. LPP is used in investment decisions, budgeting, and portfolio selection. It helps in allocating limited funds in the best way. Example, a bank uses LPP to allocate funds between loans, deposits, and securities to maximize return while controlling risk. 4. Transportation and logistics. It is used to minimize transportation cost or delivery time while meeting demand. Example, a company uses LPP to find the cheapest way to transport goods from factories to warehouse. 5. Project management. LPP is used to plan and schedule tasks and resources efficiently in projects. Example, A construction company schedules tasks like foundation, wiring, and painting to complete a building on time and within budget. 6. Human Resource Management. LPP helps in employee scheduling, workload distribution, and training plans. Example: a hospital uses LPP to schedule doctors and nurses so that all shifts are covered without overworking staff. Conclusion: linear programming is a versatile tool used in production, marketing, finance, logistics, projects, and HR. It provides managers with a scientific way to make decisions, ensuring optimal use of resources, cost reduction, and profit maximization. Tip to remember: think of LPP as a decision-making compass that points toward maximum efficiency in any managerial area. Next important long question is: 2. Discuss the guidelines for formulation of LPE. Guidelines for formulation of linear programming problems, LPP. Formulating a linear programming problem, LPP, correctly is the first step to solve it efficiently. There are some simple guidelines to follow. 1. Identify the decision variables. Decision variables represent the choices or actions to be determined. Example: a factory producing chairs and tables will have X is equal to number of chairs and Y is equal to number of tables as decision variables. 2. Define the objective function. The objective function is what we want to maximize or minimize, like profit, revenue, or cost. Example: maximize profit Z is equal to 500X plus 800Y, profit from chairs and tables. 3. Identify the constraints. Constraints are limitations on resources such as materials, labor, or money. They form inequalities in the model. Example: would availability 5x plus 8y less than or equal to 200 units, labor hours 2x plus 3y less than or equal to 100 hours. 4. Include non-negativity restrictions. Decision variables cannot be negative because negative production or resources are impossible. Example: x greater than or equal to 0, y greater than or equal to 0. 5. Check for linearity. All relationships must be linear. Multiplication or exponents are not allowed. Example: profit is equal to 500x plus 800y, linear, but profit is equal to 500x superscript 2 plus 800y, non-linear, is not allowed. 6. Ensure a realistic model. The model should represent the real problem accurately. Unrealistic assumptions may lead to wrong solutions. Example: don't assume unlimited market demand if customers are limited. 7. Simplify complex problems. If the problem is too large, simplify by focusing on major constraints and objectives to make the LPE manageable. Conclusion: formulating an LPE carefully is half the solution. Following these guidelines: decision variables, objective function, constraints, non-negativity, linearity, realism, and simplification ensures a clear and solvable model. Proper formulation saves time, avoids mistakes, and provides managers with a scientific way to make optimal decisions. Tip to remember: think of LPE formulation as building a map before starting a journey. A correct map ensures you reach the best destination. Next important long question is: 3. Solve a problem on LPP using graphical method. Problem: a factory produces chairs, kiss smiley, and tables, Y. Profit: 500 rupee per chair, 800 rupee per table. Constraints: 1. Would 5x plus 8y less than or equal to 200 units. 2. Labor: 2x plus 3y less than or equal to 60 hours. 3. Non-negativity: x greater than or equal to 0, y greater than or equal to 0. Objective, maximize profit Z is equal to 500x plus 800y. Step 1. Identify variables and objective function. Decision variables, x is equal to chairs, y is equal to tables. Objective function, z is equal to 500x plus 800y, maximize profit. Step 2. Graph the constraints. 1. Would 5x plus 8y less than or equal to 200y is equal to 200 5x 8. X is equal to 0, y is equal to 25. Y is equal to 0, x is equal to 40. 2. Labor, 2x plus 3y less than or equal to 60, y is equal to 60, 2x, 3. X is equal to 0, y is equal to 20. Y is equal to 0, x is equal to 30. 3. Non-negativity, x greater than or equal to 0, y greater than or equal to 0, first quadrant only. Plot these lines on a graph. The feasible region is where all inequalities overlap. Step 3. Find corner points. The feasible region is a polygon. Find intersections. 1. Intersection of wood and labor. Solve 5x plus 8y is equal to 200 and 2x plus 3y is equal to 60. Multiply second equation by 5. 10x plus 15y is equal to 300. Subtract first 10x plus 15y, 5x plus 8y is equal to 300 to 205x plus 7y is equal to 100. Solve x is equal to 16, y is equal to 4. 2 other corners 0, 0, 0, 20, 30, 0. Step 4. Calculate profit at each corner. Corner x, y, z is equal to 500x plus 800y. 0, 0, 0. 0, 20, 16,000. 30, 0, 15,000. 16, 4, 9,000 plus 3,200 equals 12,400. Maximum profit is equal to 16,000 rupees at 0, 20. Conclusion. The factory should produce 0 chairs and 20 tables to get maximum profit. Next important long question is 4. Explain the procedure for converting a primal LPE into its dual. Procedure for converting a primal LPP into its dual. In linear programming problems, LPP, every primal problem has a dual problem. Converting a primal into a dual is useful because sometimes the dual is easier to solve or gives additional insights. Step 1. Identify primal form. The primal problem can be of two types. Maximization objective is to maximize profit. Minimization objective is to minimize cost. Example primal maximization. Maximize z is equal to 3x plus 5x. Subject to 1. X plus 2x less than or equal to 8. 2. 3x plus 2x less than or equal to 12. 3x, x greater than or equal to 0. Step 2. Assign dual variables. Assign a dual variable to each primal constraint. For the example, let y and y correspond to the two constraints. Step 3. Convert objective function. If primal is maximization, dual will be minimization. The dual objective function is formed using the right-hand side, RHS, of constraints. Example, minimize w is equal to 8y plus 1 to y. Step 4. Convert constraints. Each primal variable gives a dual constraint. Coefficients in primal become coefficients in dual constraints. For less than or equal to constraints in primal, maximization, dual constraints will be greater than or equal to. Example 1. Y plus 3y greater than or equal to 3 from x. 2. 2y plus 2y greater than or equal to 5 from x. Dual variables y, y greater than or equal to 0. Step 5. Apply non-negativity conditions. All dual variables must satisfy non-negativity if primal constraints are of type less than or equal to. Step 6. Write the dual problem clearly. Dual of the example primal. Minimize w is equal to 8y plus 1 to y. Subject to 1. Y plus 3y greater than or equal to 3. 2. 2y plus 2y greater than or equal to 5. 3. Y greater than or equal to 0. Conclusion. Converting primal to dual helps analyze resource costs, find bounds on profit, and sometimes solve the problem more easily. Following these steps, identify type, assign dual variables, convert objective function and constraints, and ensure non-negativity makes the process systematic and easy to remember. Tip to remember: think of primal as profit perspective and dual as resource cost perspective. They are two sides of the same coin. Next important long question is 5. Describe the simplex method of solving LPE with suitable example. Simplex method for solving LPE. The simplex method is a mathematical procedure used to solve linear programming problems, LPP, with more than two variables, where graphical methods are difficult. It helps find the maximum or minimum value of an objective function while satisfying all constraints. Steps of the simplex method. 1. Convert LPP into standard form. Convert inequalities into equalities by adding slack variables. Ensure all variables are non-negative. Example. Maximize z is equal to 3x plus 5x. Subject to 1. X plus 2x less than or equal to 8x plus 2x plus s is equal to 8. 2. 3x plus 2x less than or equal to 12. 3x plus 2x plus s is equal to 12. 3x, x, s is greater than or equal to 0. 2. Set up initial simplex tableau. Columns represent variables, x, s, s, rows represent constraints. Bottom row represents z row, objective function. 3. Identify pivot column and pivot row. Pivot column, most negative value in z row, for maximization. Pivot row. Minimum positive ratio of RHS divided by pivot column value. 4. Perform pivot operation. Make pivot element 1 and others in the column 0 using row operations. Update tableau to find new basic feasible solution. 5. Check optimality. If there are no negative numbers in Z row, for maximization, the solution is optimal. Otherwise, repeat pivot steps. Solution of example. Initial tableau gives basic solution, s is equal to 8, s is equal to 12, x is equal to 0, x is equal to 0, z is equal to 0. After iterations, x is equal to 4, x is equal to 2, z is equal to 34 plus 52 equals 22, maximum profit. Conclusion. The simplex method is systematic, accurate, and useful for LPE with multiple variables. It ensures that managers maximize profit or minimize cost efficiently while considering all constraints. Tip to remember: think of the simplex method as a step-by-step ladder, moving from one feasible solution to a better one until the best solution is reached.